In this video, we're going to go through all of the graphs or the types of graphs that you need for this NCEA Achievement Standard 91257 Applied Graphical Methods in Solving Problems. So I'm going to be going through the types of graphs, when you would use them, what to look out for, what the markers are looking for, and doing a few problems for each. Okay, that said, let's do it to it. So the first one you need to know is linear graphs. Linear graphs are straight lines, essentially. So when we have our XY Cartesian coordinate system, X and Y, it's going to be a straight line. So this is always the classic way of expressing this as an equation is Y equals mx plus c, where m is the slope or the gradient of the line. So if this is 1, this is going to be m. I do a whole bunch of these, but you should know these pretty off by heart. If m is a positive number, i.e. it's greater than 0, it's going to slope upwards. If m is a negative number, it's going to slope downwards. If m equals 0, it's going to be a flat line. Okay. So when would we use this? We would use this when you see words such as for every such and such, by the same amount, things like that. It's going to be fairly obvious which one you're going to use. Yeah. So what do we know about this? What is the domain and what is the range? Well, the domain, for our purposes for this video, we're going to say that the domain is all the possible x values. That isn't quite true, but at this level, that is pretty much what we mean. So we need to ask ourselves, is there a value of x that we cannot use? And in all but one type of example, the answer to that is no. So the domain of this is a subset of all the real numbers. So there's no x that we can't put in there that we don't get an answer for. The exception is when we have something like x equals 3 or x equals 2 or something like that. In that case, say x equals 3, that would mean that regardless of what y is, x equals 3. Well, the domain for this is just 3. But that's kind of an exception to the rule. It's not technically a function, it's a relation, but you get the point. That's kind of the exception that proves the rule. Everything else, the domain is all possible numbers that x can equal. What's the range? Well, for this video and for this standard, we're going to say that the range is all the possible y values we can have. And what's the range for this? The range for this, y is going to be equal to, y is going to be a subset, I should say, of all the real numbers. So all x will yield a y. The exception to that is, again, a perfectly flat line. So this is our XY coordinate system. Something like that which is parallel to the x-axis. Of course, it's only going to have one value. So this is, say, y equals 2. The range for this would be y equals 2, and that's it. But again, that's the exception to the rule. Okay. The other part of the equation, so if we look at the classic way of expressing this, that plus c is, of course, going to be the y-intercept. So if c is 0, it crosses at the at the origin point. And for all of these, to find the x-intercept, that is the root, we set y equal to 0 and solve. Okay, so if y equals 3x plus 2, and we want to know what that's going to look like, well, it's going to cross the y-axis there at 2, and it's going to go up in kind of lots of 3. So every one that it goes across, it's going to go up by 3. But what's going to be the x-intercept? Well, we're going to set y equals 0 and then solve for x. So y equals 0. So therefore 0 equals 3x plus 2, and it's now no longer a graphing problem, it's an algebra problem. I'm going to take this 2 across, I'm going to subtract it from both sides. So negative 2 equals 3x. So x is going to be equal to negative 3 over 2. So this one here is negative 3 over. Okay. When can we develop to say that we have a straight line? So I give you the straight line here. We're going to do kind of the reverse of what we did before. And I say that the straight line goes like that, and it goes between the point, what's that going to be? Say 5, 10, and one of the other points is 1, 3. The straight line goes through both of those points. What is going to be the equation of that line? Well, for that one, we're going to make this, the way I'm going to do it, I'm going to make this 0.1. I'm going to make that 0.2. So this is the x that belongs to 1. This is the y that belongs to 1. This is the x that belongs to 2. This is the y that belongs to 2. So the gradient, so this is one that you should know. The gradient is going to be y1 minus y2 over x1 minus x2. So for this, it's going to be y1 is going to be 10 minus y2 is 3, divided by x1, which is 5, minus x2, which is 1. So 7 over 4. Okay, now that we've got that, the next equation that you need to know, y minus y1 equals mx minus x1. And the y1 and the x1 are going to be the same, and the m is going to be from here. So y minus y1 is y minus 10 is 7 over 4, x minus 5. So y is going to be equal to 7 over 4 x minus 35 over 4 plus 10, whatever that is. Okay. The other thing that we need to know, we need either, to find the equation, we need either 2 points, a minimum of 2 points, or we need the gradient and one other point, which is pretty much what we have here, the gradient and one of the points. Okay. How do we do this on our calculator? So say we have the 2 points here, 5, 10, 1, 3. What we're going to do is we're going to go to menu, then we're going to go to stats mode. And we're going to do a linear regression. So I'm going to put in 5, xe, 1, xe, and I'm going to go across, and I'm going to put 10, 3. See how these ordered pairs are the same as the ordered pairs here. Okay, then I'm going to graph it, graph 1, and I'm going to calculate, and I'm going to calculate a straight line here, and here we go. That's the equation for that line, which is exactly what we had before, and it works it out for us. Okay, so in other words, this line is going to be 1.75, which is 7 over 4, x plus 1.25, which is 35 over 4 plus 10. And we know that it's a perfect regression because r squared and r are both equal to 1. Okay, let's do some examples. So this is a fairly typical question. Two phone companies charge the following monthly costs. So they're Plan A and Plan B. This is going to be the flat fee that they charge, and then they're going to charge 12 cents per minute, and this lot charges 6 cents per minute, where T is the number of minutes per month and A and B are the monthly costs in dollars. Graph both equations on the same axes for 0 T between or equal to 0 and 500. Use this graph to find the number of minutes where both plans cost the same, and explain which plan is better for someone who uses fewer and which one is better for someone who uses more. So I'm going to use GeoGebra for this. I love using GeoGebra mostly because it's free. So for this one here, we're going to replace T with X because this program is in X. So let's do this. So this is plan number A. So this is A plus 0.12 X. You can see that's going to be a straight line when I zoom out. There it is there. So it wants it between 0 and 500. So let's zoom out even more till we get 500. There we go. There's 500 there. So we only want between 0 and 500 for this one. So the green one is plan A. Plan B was 40 plus $0.06 times X. And we see there where they cross, that's where we're going to have our answer where they're the same cost. So I'm going to look at that, and that's at 200. So they cross, therefore, at 250. So we've done that on GeoGebra, and they cost where T is 250 minutes. Explain which plan is better for someone who uses fewer. So if we go into GeoGebra again, the green plan is better for people who use fewer, and the blue plan, which is plan B, is going to be better for people who use more minutes than that. I mean, if you're talking 250 to 500 minutes a month, wow, okay. So A is better for people who don't talk much anyway, and B is better for people who yabber on. Like my favorite line in the Maltese Falcon.
You talk if you like. I tell you right out, I'm a man who likes talking to a man who likes to talk.
Okay, the next one is a taxi. Taxi company charges a fixed starting fee plus cost per kilometre. This fare is modelled by the cost is 4.50 plus 2.80 times D, where D is the distance in kilometres and C is the cost in dollars. Graph the fare for distance between 0 and 20 kilometres. So I've done this on GeoGebra, which I'll show you now. So this is 4.5 plus 2.8x. So there isn't an option to change this to a D. So I'm going to say that's X. It's going to be the same shape. And here is 20. So after $20, go $20, it would 20 kilometers, it would cost $60. Explain what the gradient and the y-intercept mean. So the y-intercept is 450. So the y-intercept is going to be the fixed starting fee. So when you get a taxi, as soon as you get in the taxi, for the privilege of getting into the taxi, they charge you a fee, and then they charge you for the distance that you cover. The gradient is going to be, so the gradient is going to be the price per kilometre, presuming that the taxi's meter is all kosher. The customer has $35. Use your graph to estimate the distance they can travel. So we could do that algebraically, but we'll do that we'll do that graphically. So they have $35. So $35 is here. And if we go down, just the questions again, they have $35. Okay. They have $35 and they want to know how far they can go. We're going to go across there, and that's going to be at, what is that, about 11 kilometers. Okay. If we were to do that graphically, algebraically, it would be 35 is going to be equal to 4.50 plus 2.8 D, and we would solve that for D. The next type of graph is one that you should be pretty familiar with. It's the good old parabola. There are two ways of expressing this parabola that you need to know. The first one is the sort of quadratic one that you should already know and love. You should have done that already. The second one, so this is quadratic form, quadratic equation form. The other one is turning point form, and that is expressed like this: x minus h plus k. So what exactly do these h and k mean? The turning point, that is that point right there, or that point right there, the maximum or the minima is at the point, so the turning point at hk. Okay, that also means that the line of symmetry is at x equals h. So the line of symmetry for this one here would be sort of a mirror line that goes through that turning point. Again, if a is greater than 0, it's going to look like that. If a is less than 0, it's going to look like that. Okay. What are the range and the domain? So the domain, what are the possible values of x? Well, x is just going to be a subset of all the real numbers. There's no x that we can't put in there that's not a real number. The range, though, is not all values. So that's going to be y, which is equal to or greater than k if a is greater than 0, and it's going to be y less than or equal to k if a is less than 0. So we have a less than 0 here. All the values of y is going to be everywhere from here downwards. We can't have anything up here. And likewise, if the graph is like that, and this is k here, the values of y must be everything above that. So this is k there, and this is k here. Okay, let's do some examples. So how could we work out the equation of a parabola if we are just showing it? So for this, there's two scenarios where we can do that. Either we need 3 points, or we need the turning point and one other point. Again, we're going to presume that we're not going to use calculus for this. We're just going to use graphing methods. Okay, let's have a look at one that goes through 3 points, and I'll show you how that's done. Let's say, for argument's sake, that we're told that a parabola passes through the points -1, 3, passes through the origin point, and it passes through the point 2, 4. How would we solve that? Well, we would go to the original equation, and that really tells us that whenever x equals -1, y must equal 3. And whenever x equals 0, y equals 0 as well, and so on. And we would take this original equation, y equals ax squared plus bx plus c, and we would substitute these values in, and we would be able to use a system of simultaneous equations to find out what a, b, and c are. Now, I don't have the patience to do that. I'll leave that to you to do that, but I'll show you how to do that quickly on your calculator. What we're going to do, we're going to come along to stats mode again, and we're going to do pretty much exactly what we did for the linear values. In fact, it's still set up there on this calculator. -1, 0, and 2. And then we're going to go across and we're going to complete those ordered pairs. 3, 0, 4. And then we're going to graph 1, and here we see the 3 points. We're going to calculate, instead of a linear function, we're going to have a parabola x to the power of 2. So it's going to look like that. So this graph is going to have the form y equals 1.66666 x squared minus 1. So in other words, 1 2/3 x squared minus 1 1/3 x plus 0. Okay, let's say that we're told that a graph has a turning point at 3, 5, and it goes through the point 2, 1. Okay, so what are we going to do there? Well, we know we've got a turning point, so we can use turning point form. So we can use y equals a, and that a is going to mean something now, h squared plus k. Well, we know that k is going to be 5, and we know that h is going to be 3. We don't know what a is, but let's put it in and work out what a is going to be. So y is going to be equal to a, and when x minus 5 squared plus, no, it's the other way around, x minus 3 squared plus 5. That's going to be our equation that we're going to work with to find a. We know that when x equals 2, y is going to be equal to 1. So 1 is going to be equal to a, 2 minus 3 squared plus 5. Now we have one equation and one unknown. So 1 is going to be equal to 2 minus 3 is -1. -1 squared is 1. A plus 5. Therefore, a must be equal to -4. So therefore, our graph has the equation that meets this little set of requirements, is going to have the formula -4 x minus 3 squared plus 5. And in fact, let's put it in a calculator and see that actually does go through this point here. So I'm going to go to menu, and I'm going to go to graph mode, and I'm going to put this in, -4 brackets x minus 3 squared plus 5, and then I'm going to draw it, and it's going to look all wonky. And then I'm going to zoom out a bit. Okay, and now we're going to find what is the y value when x equals 2. So we're going to go to gsolve, and then we're going to go across y calculate. When x equals 2, y should equal 1. And in fact, that's exactly what we get. So the first example here is another classic problem. It's a ball thrown into the air. The height of the ball is modeled by the height as a function of time, so -0.5 t squared plus 4t plus 1, where h is the height and t is the time in seconds. Graph this function for 0 to 10 seconds. So I've gone along to GeoGebra and done it. So again, you can't have t, you can only use x on this, but it's going to have the same shape. 0.5x squared plus 4x plus 1. So here we throw the ball in the air, so we must have thrown it into the air 1 meter above the ground. It's gone up and it's come down here and it's landed in, what is that, about 8.25 seconds later. So this looks around about 4 seconds into the throw, and the maximum height is going to be 9 meters. So find the maximum and the time. So it's when t equals 4. So t 4 seconds after it, and the maximum height is 9 meters. Use a graph to estimate when the ball hits the ground. So we kind of did that without even realizing it. It's going to hit the ground at around about 8.25, because this is 8.2, this is 8.3. So around about 8.25 seconds. Okay, explain why the negative values of t are not useful. So the ball isn't moving before we throw it. So therefore it's not going to have that shape. So therefore it's pretty pointless trying to put that on the graph. It's going to be kind of whatever we hold it, then we throw it in the air, and then it hits the ground, and then time ends. So the world begins when we throw this ball. The second one is also a classic problem. We have an archway as modeled by this equation, where the height of the archway is this. So this is in turning point form. So we know that it has a maximum, because this is a negative number, at 4, 5. But then it says that x is the horizontal distance in meters from the left side, and that's going to be important. Graph the arch. So here's one that I prepared earlier. So there it is there. Now notice something really strange here. It says that x is the horizontal distance from the left of the arch. So I'm kind of taking that the arch kind of stops here and kind of has that shape, and it goes up to the maximum height there, and then kind of lands there. That's what I'm taking it, because you can't have something that's beyond the left hand side. So I'm going to take it, it's kind of this kind of funky shape here, where this, so those state the maximum height. Well, we already did that, so it's going to be in the middle there at 4 meters, and that's going to be at 5 meters in height. How wide is it? Well, from here, the left hand side, to here, it looks like it's about 8.5. So we're going to say that the distance from here to here is 8.5. And again, it's graphical, so we're going to need to do it by eye. Okay, then it says a truck is 3.8 meters high and 2 meters wide. Decide whether it can pass through the center of the arch. So if it's 2 meters wide, and this is the center of the arch here, so 2 meters, our truck, the left hand side of the truck is there, the right hand side of the truck is here, and it goes up 3.8 meters. So 1, 2, 3, 4 meters, 4 meters is there, and our truck is 3.8 meters. So our truck is going to kind of look there like that. So that here's the wheels, the left wheel and the right wheel is the kind of the door and the number plate. Maybe a little smokestack. Yeah. So we're looking at it from behind as it goes into the tunnel. So yes, it does fit. The next type of graph that we're going to be looking at is the cubic. So a cubic is kind of like a parabola with an extra x in a way. So we can write it one of two ways. We can either A, x cubed plus bx squared plus cx plus d. Or the other two ways that we're really interested in, y is a x minus h cubed plus k, where we have a point of inflection at h comma k. So point of inflection is, for our purposes, is where it's flat. It's not really, it's where it stops being concave and becomes convex and vice versa. But that's all we're going to say. So our graph is going to have either one of two looks. It's either going to look kind of like that, where that's our point of inflection, or it's going to kind of look like that. It's a bit exaggerated, where that's going to be our point of inflection. A is going to decide which of these it is. But notice something interesting. If we change H will move it to the left or the right. Changing K will move it up or down. Now, if we add to K, it's going to move up. It's going to translate up. If we subtract from K, it's going to move down. If we want to move to the left, we want to add to H, and to move it to the right, we want to subtract from H. It's kind of the other way, counterintuitive. And this is the same for all of the other graphs that have H and K in them. Okay. Once we've done that, we need to decide what A is going to be. So for this, if we have the turning point, if we have this point of inflection, we have this POI, point of inflection, we would put in a point and we would find A. So let's do it on GeoGebra so you can see what that's going to look like. So here's one that I did just before. I've let A be 2, I've let H be 3, and I've let K be 4. So it's in that same form there. Turning point, our point of inflection is here, and sure enough, it's at 3, 4. Now watch what happens if I change this 2 from a positive 2 to a negative 2. It's flipped. It's kind of 180 degrees flipped around that point of inflection. So I'll take it back and go back. Watch what happens when we subtract 2 more. So we're going to say instead of negative 3, it's negative 5. It's going to move to the right 2 places. If we want to move it up 2 places, we're going to add 2 to that, and it's moved up. Let's just grab it and move it across. Okay, let's do some questions. Right, before we do that though, there is another form of qubit that you need to know, and it's going to be in this form here. So y equals a x minus p, x minus q, and x minus r. And this is in our root intercept form. So in other words, this is going to be our cubic, and it's going to, if it's that sort of shape, it's going to be at P, Q, and R there. And again, if we know one of the points, we can find out what A is above 0, it's going to look like that. If it's less, it's going to look like that, but they're going to cross at the same place. So let's do a couple of questions. Question 1 says that we have a curved path in a park, and it's modeled by that equation there, where x and y are the distances in meters. Graph the function from negative 4 to 8. So I've done that already on GeoGebra, which I'll just bring up now. So sure enough, we see that value here. Then it tells us to describe the shape of the graph. Well, the shape of the graph is a cubic where, I don't know, it's kind of a lazy S, a lazy N shape with a point of inflection at 2, 1. State the point where the basic cubic has been shifted to, well, to 1, and explain how the graph has transformed from the graph y equals x cubed. So here is x cubed here in grey. So what's happened? Well, this is the original graph y equals x cubed. We've kind of spread it out. We've kind of made it a bit of a lazier shape, and we've moved it to the right 1 and up. We've moved it to the right 2 and up 1. Otherwise, it is the same kind of shape, but less extreme. Eccentric, I think, would probably be the word. So now we're asked to draw this graph here, y equals x minus x plus 2, x minus 1. In fact, I'll make that a bit bigger, better. Y equals x plus 2, x minus 1, x minus 4, all in brackets. Graph the function. Well, here's the function here. Find the x-intercepts. Well, the x-intercepts are going to be really easy. It's going to be -2, +1, and +4. -2, +1, +4. Find the y-intercept. Well, it's going to be all of those multiplied together. 2 times -1 times -4 is +8, and that's what it is there. Explain how the factorized form helps you identify the x-intercepts. Okay, so remember our rule. To find the x-intercepts, we make y equal 0 and then solve for x. And this equation is x plus 2, x minus 1, x minus 4. Okay, we're going to make y equal 0. So that tells us that we have three things multiplied together to give us 0. Well, the only way that that can be true is if this equals 0, this equals 0, this equals 0, all of them equal 0, or 2 of them equal 0. We're going to say that all of them equal 0, so therefore it crosses the x-axis where x plus 2 equals 0, so x must equal -2, which is what we have. X minus 1 equals 0, so x equals 1, which is what we have right there. Let's move it up a bit. And where x minus 4 equals 0, x must equal +4, and that's exactly what we have here. So again, to find the y-intercept, just to prove that it is 8, remember to find the y-intercept, we set x equals 0 and then solve for y. So y is going to be equal to 0 plus 2 times 0 minus 1 times 0 minus 4, and that equals +8. So y equals 8. Okay. Okay, the next type of graphs that we're going to deal with is hyperbola, which is not to be confused with hyperbole, which is a deliberate exaggeration in English. Exaggeration. So this is a maths one, not an English one. So hyperbola is in this form. So you see the h and the k making another place. So changing h is going to move it left or right. Changing k is going to move it up or down. So what is this going to look like? Well, the a here is going to change the shape. The h is going to move to the left or right. K is up or down, like I said before. The best way to look to sort of work out what's going on here is to do one. So let's choose a is 2. Let's choose h as 3, and let's choose k as 4. And let's graph it. So here is that same graph here. You see it has this kind of really distinctive form. Now, 2 things we need to know here. There is an x and a y intercept. There doesn't have to be a y-intercept. There does have to be does there? No, there doesn't have to be an extra y. And for the reasons that I'm going to tell you now, the vertical asymptote here is going to be when x equals h. So if I do x equals 3 here, x equals 3, you see that there's an asymptote. Remember, an asymptote is a value that the graph will get arbitrarily close to, like that, but never quite gets there. So if we go on and on and on and on and on forever, it's going to get really, really close to it, but never quite get there. So it also has a horizontal asymptote, which is going from left to right, and that's when y equals 4. So when y equals k, in other words. So again, this is going to get arbitrarily closer and closer to the asymptote, but never get there as we go to negative infinity. And then as we go out here towards positive infinity, it's going to get arbitrarily close to it from above, but never quite get there. So we can make the general rule that the vertical asymptote is going to be where x equals h, and the horizontal is going to be where y equals k. Okay, let's go back to the original equation and see what happens when we change these values around. So what's going to happen when we change the 2 around? So let's change it from a 2, let's change it to something like, let's change it to 3. So watch what happens. Not a lot's going to happen. It's going to be pretty subtle, but the shape is going to change. It's going to change a little bit. Let's do something really drastic. Let's change it to 30 and see what happens now. And it's going to kind of pull these things apart. They're going to be bigger. The scale is going to be much bigger now. Okay, let's go back to 2. So remember our rule when we change, let's come back in here. When we change the h value down the bottom here, it's going to move left or right. So let's change it from -3. Let's change it to negative. Where is it going to go from here? Well, it should move to the right 2 places. Sure enough, that's what it does. And now when we change the k value, don't want to do that. Instead of 4, let's change that to 7. So this should move it up another 3 places. So let's do that, and sure enough, it moves up 3 places. So in order to find the x and the y intercepts, there's no real hard and fast rule for this one. Just note that if h equals 0 or k equals 0, the one of the asymptotes is going to be on the axes themselves. But the only way to do it again is to find the x, we set y equal to 0 and solve, and to find the y-intercept, we set x equal to 0 and solve. So why is there a vertical asymptote when x equals h? Well, remember what we can't divide by. We can't divide by 0. When h equals x, x minus h is going to be equal to 0. Which means that if h equaled x, then we would be dividing by 0, and we can't do that. Not allowed. But we can get arbitrarily close to it, but never get there. Okay, let's do some questions. Those of you who do economics should recognize this question. It's the law of diminishing marginal returns. So the time taken to complete a job is modeled by t equals 60 minus n, where t is the time in hours and n is the number of workers. Graph the function between 1 and 20. So I've done that right here. So here is 1 here. So this one person is going to be, it's going to take them kind of 60 hours to do it. And if we had 20 workers, it's going to take them 3 hours to do it. Use the graph to estimate how long the job takes with 8 workers. So we're going to come on here to 8. Across there, so there is 8. And it's about halfway between 5 and 10. And remember, we can split an hour into pieces. We can't split people into pieces. So we're going to say that's around about 7.5 hours. Estimate how many workers are needed to finish the job in 5 hours. So we're going to come along here to 5. 5 hours would require 12 workers. Explain why n equals 0 is not possible. Well, you can't, if the function is over n and n was 0, we would have 60 divided by 0, and we can't do that. But what would it mean? It would mean that this job would take infinitely long to do. Infinitely long to do. Okay, we would never finish it because no one would be doing it. Okay, next we're given a hyperbola, and now it's got h and the k. So h is going to be 2 and k is going to be 3. Graph the function. So I've done that here. Bring up GeoGebra. So here's the function here. Then it says to state the vertical and horizontal asymptotes. Well, the vertical asymptote, remember, it's when x equals h, which is that one there. And the horizontal is when y equals k, which is going to be that one there. All right. State the domain and the range. Well, if there's a vertical asymptote, x equals 2, then the domain, as far as we're concerned, like our definition of a domain, x is going to be all real numbers not equal to 2. The range, again, this is the y values. Y values is going to be all real numbers not equal to 3. So it's going to get arbitrarily close to 3 but never get there, and x can get arbitrarily close to 2 but never quite get there. That's what an asymptote is. So that's the end of part 1. Tune in to the same back channel where we do part 2. We do slightly more obscure graphs that you may or may not need.
You know, I have one simple request, and that is to have sharks with frickin' laser beams attached to their heads.